Okay, so picking up. For this second video, we're going to pick up where we left off. Before we talked about sort of a general overview of web development and then went through the rendering, HTML, Canvas, WebGL, different ways that you can present the information to the user. Now we're going to talk about scripting. So this is part of this first 3 videos will be rendering, presentation, the one we already did, scripting this video, and then transport, how data is transferred back and forth. It's just sort of going over what tools the browsers give us, the workspace that we're working in, before we start diving into different approaches, different frameworks in any kind of detail. So let's go ahead and start with why we need scripting. So I have kind of just a simple example here where I went to Stack Overflow, I typed the word scripting, and a bunch of tags pop up. I didn't think about it, but I'm not logged in. So here I scroll down, things are moving around. There are some ways to do some basic movements without scripting, but generally any type of interactivity in a website is going to be provided by scripting. So for example, as I click the different things here, it's changing what gets displayed here. This is normally done by scripting. We'll talk at the end about how that might not be the case. But basically, when the web first started out, it looks very much like Wikipedia still looks today, which is you have your page, it gets laid out there with HTML and CSS, and that really the only interactivity is clicking links to jump around different parts of the page. Now, even Wikipedia has given in and done some scripting, because as we can see, as I hover over a link here, it pops up and displays some of the link itself. So that is scripting. So when HTML and HTTP first came out, the idea was, okay, if we need any more sophisticated behavior than the ability to click links, you could also create forms and post some basic data in forms without any kind of scripting. But anything beyond that, any custom behavior, you'll need scripting. And the trick with scripting is that if we go back to our original picture here, the scripts themselves are running in the browser on the other side of the internet from the server. So when you are browsing the internet and JavaScript is enabled, the server is sending scripts, code. That code runs on your machine. So for example, if you wrote a script to eat up all of the memory and just run in an infinite loop and someone visited your web page, that script would run on their machine. Now, you probably can't exactly write such a script, and we'll talk about that in a minute. But that's the idea with scripting. We need a way to run code at the user's browser on the other side of the internet to control things. And the basic thought was these types of behavior, this type of interactivity is too fine-grained to really be going back and forth to the server for every single type of control. I mean, if you want to go for the far other end, you have something like the Remote Desktop Protocol, RDP. If you remote desktop into a machine, there's really no scripting whatsoever. You're just sort of, everything's being done on the remote machine, and you're just viewing a video of what's happening. The internet is somewhere in between. Some stuff happens on the backend server to prepare your data, prepare your HTML and stuff like that. It'll get sent across, and then there's scripting that runs in the browser. There's lots of different styles as to how much scripting versus how little scripting, but let's go ahead and move on. As before, there's a couple of different choices. There's JavaScript, there were applets, and there was Flash, but as we talked about, those died off. And coming out now, there is WebAssembly, and we'll talk about that some too. Why scripting? Kind of just went through this. Scripts allow for manipulation of the DOM. Outside of the limited model. What I mean by that is HTML allows for links and some simple things like, there used to be a marquee element in HTML which would create scrolling text that you would see on all kinds of GeoCities pages back in the day. So that model is pretty limited, and HTML was never intended to be a full-fledged GUI framework where you write all of the GUI's behavior in HTML. And I mentioned on here a couple of things. Oh, Discord. So just to kind of show, even today, you might have some sites like Wikipedia, which still have very little scripting. If I look at it, go ahead and reload it. These are all the resources it loads. And there's only 2 scripts that get loaded, and they're about 70 kilobytes, which is still substantial. But if I go to Discord and I do that same thing, I'm not even logged in yet. And if I load it, then there are many scripts, and some of them are as large as 1.6 megabytes. So Discord uses a whole lot more scripting than Wikipedia, and Discord is a whole lot more interactive than Wikipedia. That doesn't mean that every modern website is going to use more scripting. As I said before, there are a bunch of different approaches for how you create an interesting and exciting website. But there was a trend called Web 2.0, and I mention it because you'll hear about it sometimes. It was really big, probably 10 years ago now, maybe. I guess I'm getting old. Yeah, probably around 10 years ago. Everything had to be Web 2.0, and the big new thing was going to be Web 2.0. And it was never very solidly defined. This interesting article here kind of tries to go through, but generally Web 1.0 was very static pages, didn't have a lot of scripting. Here it mentioned that kind of marquee and blink thing. And my favorite link, the first browser war. That sounds much more exciting than it really is. Web 2.0 was really Facebook, MySpace, all your social media sites start popping up, Twitter starts popping up, a lot of the really big websites that we use today, and they were all very dynamic. They used a lot of scripting. They were very interactive. There was more than just links. So if you go on Facebook, for example, you have your infinite scrolling, you have messaging back and forth, you have all of this rich behavior that HTML doesn't provide for you. So I talked a little bit about how someone could write a malicious script to kind of tie up the CPU. And that's probably still possible. Tying up the CPU is generally seen as, okay, if you visit a website by accident and they write a script that freezes your browser, well, close the browser, restart it, don't go back to that site. That's generally seen as a acceptable use case. What would be unacceptable, though, is if you accidentally went to some website or you clicked the wrong link and that website then immediately downloaded a virus to your computer and turned your computer into part of a botnet, or that website just decided to remove your entire C drive, start deleting all of your files. Those things would be very bad. Generally, with the web, it's assumed that people are going to be somewhat reasonably intelligent, but at the same time, sometimes you'll visit websites you don't entirely trust, and sometimes bad things could be attacked at you. That's a bad way of phrasing that. Sometimes you'll visit websites you don't entirely trust, and you don't want those websites to be able to destroy your computer. So one of the big requirements for a browser is to have a good sandbox. And the sandbox means a little area that your scripts are allowed to play in where they can kind of access the real world, which in this case is the rest of the operating system, but not really. So the idea is you have your browser, and as we've talked about before, you have your DOM, which is in memory, and your browser wants to be able to run scripts. Your browser is running on the operating system. Your browser has full access to the operating system. If Chrome wanted to, it could wipe out all of your documents. But the Chrome is hopefully something you can trust. You'll often see in security documents and things like that, browsers are called trusted user agents. Generally, you should never use a browser you don't trust. Never download any executable you don't trust. But we assume the browser is trustworthy. We don't assume the scripts are. So the browser's job is to keep the scripts from being able to destroy your computer. But at the same time, the scripts still need to access some features on the OS. maybe audio, maybe the file reader. So file reader, if you want to upload a file, upload a video to YouTube or something like that, you need to be able to access the OS to get that file. And that's all going to be done in YouTube's scripts. Chrome isn't really responsible for that. So Chrome has to create an API. The file reader API is one example, where it allows access to the OS, but it's limited access. So the file reader API doesn't allow you to, for example, view all the directories on a machine or list the contents, list the files that are in a directory. In fact, the file reader API only allows you to upload files if you've used Chrome's file chooser to select the file. So when you visit a website, you can see a lot of custom elements that look very unique and different. But the file chooser is almost always going to look the same because it's provided by the browser. And so anyway, and that's part of this whole sandbox mechanism, which is to prevent your scripts from having unlimited access. So you might want them to have access to WebGL, but you can't give them full access to the OS. So now you have to create an API. So browsers have a lot of work to do creating and maintaining these secure APIs and maintaining the sandbox. And it's actually a really hard thing to do. And you really only see it in browsers. So this is one of the challenges for why can't I just write my scripts as C#? Why doesn't the browser just support launching C# and running C# code? Or why doesn't the browser just support running Java code? And it's because several reasons, but one of the reasons is it's very hard to enforce this kind of sandbox. And so I have just an example here. This is just reinforcing that idea. C# does have this concept of app domains, and people often think that that is a fully trusted working sandbox. But they have a big caution note here saying you have to at least partially trust the code you're running, blah, 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 blah. It's not super secure. Don't use this as don't think that you have a browser sandbox and you can run untrusted C# code using app domains. So just a way of saying that creating a sandbox is really hard. That's one of the jobs that browsers have to do. That's why a lot of work goes into browsers. Also, I have just extra error here. Scripts are allowed to access the remote server to make HTTP calls. So you'd see it a lot more in something like if I go to Reddit. Reddit is constantly making calls back to the home base. And as I scroll, it has to make calls more and more to load more and more content from the home server. So your scripts do have access to the remote server. They don't have access, again, to just open up random ports and sockets. It's all protected by the sandbox. The sandbox is a pattern you'll see in other places as well. It's very similar to a virtual machine. So if you have your Java virtual machine here, you have a Java program, and then your Java program doesn't have unlimited access to the OS, you have to use the standard library to access the OS itself. Although in Java you can write native bindings, so you can get raw access to the OS, but that's so it's not meant as a security sandbox, but it's that same kind of idea. A sandbox and a virtual machine look very similar, is the point I guess I'm trying to make. And even if you have a proper virtual machine, like you would think of from VMware or something like that, it's still kind of the same thing, where you have a virtual OS and it's guarding your access to the OS. So you'll see this pattern throughout as you work on programming. So let's go ahead and start talking about some of the scripting languages. Sorry for the horrible meme here, but JavaScript is one of the web's most amazing comeback stories. So back in 2000, when I started coding, JavaScript had the same reputation as PHP and Perl do today. PHP and Perl also had a terrible reputation back in 2000, so it's not like they've gotten any better, whereas JavaScript has changed quite a bit. It was seen as slow. Any kind of scripting language is always assumed to be slow. Unpredictable. There's a lot of dangerous things you could do in JavaScript, and a lot of them were promoted as best practices by bad developers, and there were just a lot of really bad JavaScript out there, poorly written, hard to maintain spaghetti code. Primitive. There was no support for modules. That led to a lot of spaghetti code. No real support for objects, a pretty poor standard library, so on. So this is just kind of a joke that JavaScript, the definitive guide, is this thick, whereas JavaScript, the good parts, you only really need about that much. And the rest of it is just really bad ideas waiting to bite you. For a long time, it was just kind of assumed that Flash and Flex would always be the alternative. If you wanted a really interesting website, you would use Flash or Flex. Facebook and Google kind of changed that. I don't know. I like to think that Google murdered Flash. I'm not entirely sure if that's true. But anyway, Flash died. Google was looking very suspicious with means and motive. And a power vacuum arose. So this happened sometime around the late 2000s, around 2010. And since then, JavaScript has skyrocketed in just a fascinating way if you watch that kind of thing. It's no longer slow. I mean, it's arguable. Slow is a very subjective term, but it's a lot faster than it used to be. Google does a lot of really fancy compilation stuff. It's no longer primitive. There's more tooling and more libraries for JavaScript than any other language. It is ridiculous how many libraries are out there for JavaScript. Now, many of them are bad, but they're out there. And then there are a lot of good ones, even amongst the bad ones. And even amongst the good ones, you often have 2 or 3 different ways to solve your problem. Just take build tools, for example. In JavaScript, you have gulp, grunt, webpack, rollup. Even TypeScript can be used as a build tool. There's half a dozen different ways that you can solve any given problem in JavaScript using pretty decent libraries that are out there. It's still kind of unpredictable and dangerous. They couldn't really break backwards compatibility, so you can still do a lot of really terrible things in JavaScript, and there are still people out there that advocate doing terrible things. And now it's also very confusing. So it's not quite as bad as it was maybe 2 or 3 years ago, but JavaScript is still, when you have half a dozen different ways to solve any given problem, that's going to cause a lot of confusion. JavaScript now has a very steep learning curve that it never used to have before. And there's a very interesting article called Learning JavaScript in 2016 or something along those lines that you should give a read. I won't bore you by reading it through here, but it just kind of goes through some developer coming from, back in 2010 who used to write JavaScript, and then he come in 2016 and they're completely out of their depth. Everything has changed and there's just way too much information out there. So I like to show this slide. It's a very good visual. So this is Google Trends, and you can see that back in 2004, Flash dwarfed JavaScript. Angular didn't even exist back then. Right around here, JavaScript Flash was announced that it was going to die, and so Flash has since died. Around that same time, jQuery started taking off. jQuery is basically a better standard library for JavaScript. And then shortly after that, suspiciously a couple years after, or right around the same time that Google decided to kill Flash, Google also decided to come out with Angular, their big web framework. So that's been taking off lately. So now we're in a stage here where Angular is more popular than jQuery and Flash is nearly non-existent. It's a very weird place to be if you were doing any kind of web development 10 years ago. I could go on for hours, so this is my reminder to not go on for hours. Just a couple of things that you'll see out there. You'll often see JavaScript abbreviated as ES or ECMAScript, and that can be very confusing. Technically, ECMAScript is the standard, and JavaScript is the implementation. So each browser could have its own JavaScript engine, own implementation of JavaScript. But when you hear about people talking about the next version of JavaScript or something like that, they're usually talking about the next ECMAScript standard. And then browsers. So usually the way it works is ECMAScript, the ES organization, comes out with a new standard, and then all the browsers rush to catch up, and then all the browsers start doing things above and beyond what's in the standard. And so then a new standard has to be created to kind of capture what the browsers have been doing, and then everyone has to kind of jump back up to that standard. So for example, there's things out there today like being able to watch an element and get notified if it gets resized. is something that is not in the ECMAScript standard, and both Firefox, Edge, and Chrome have different implementations for it. There is now a proposal for ECMAScript, I don't know, 7 or 8 or something like that, that will standardize that, but we have to kind of wait until it gets around. So that waiting game can get very frustrating. So Babel, TypeScript, and CoffeeScript were all originally intended to solve that waiting game. The idea is, okay, I know that all 3 browsers have a different way to observe an element for resizing, but now there is an ECMAScript standard out there. It's going to take the browsers 2 or 3 years to actually start conforming to that standard. In the meantime, we'll create, they call it a transpiler, which will take in, so Babel actually takes in JavaScript and it spits out JavaScript. So it takes in JavaScript written against the next version of whatever ECMAScript standard you want to go against, and it compiles it down to code that will run on any browser using each of the browser's individual libraries for handling it. You'll see this in CSS a lot too, where each browser has some specific things and then they get standardized and then they come up with new specific things. TypeScript and CoffeeScript were, again, just 2 different approaches, although CoffeeScript saying, oh, well, since we're adding this compilation, transpilation step anyway, let's go ahead and make JavaScript a slightly prettier language. And then TypeScript took it one step further and said, oh, since we have this compilation step, instead of just making it a prettier language, let's also add support for static typing, strong typing. I'm never sure exactly what you call it, but really good type system. And so, I mean, where we stand today, TypeScript is easily one of the better languages out there. Now, I won't go on for hours. Okay, so let's talk about WASM, when you hate learning new things. So for years, people have asked, why can't I just write C++, C#, Java, whatever I already know, and have it run inside the browser? So no one, just so you know, had a brilliant insight of, oh, we can write C# in the browser and then everything will be solved. People have been trying for a long time. WASM is the latest attempt. You'll see things like Dart. There were some other attempts with Java. I can't remember the exact names of what they were, to try and compile it down to JavaScript. Various approaches that have been tried. WASM seems to have some legs to it. It's very popular right now, so we'll see how it does. Basically, the idea is to create a universal assembly language. So most assembly languages are built around a CPU and probably memory as well. And so the instructions you have available, they want to give you as many instructions as possible so that you can take advantage of all the features on the CPU. WASM is starting off with, all right, we're just going to pretend we have some kind of really basic CPU. We have a limited set of instructions. The instructions are really just instructions for doing math and instructions for moving data around in memory onto a stack and off of a stack. It's kind of similar to IL. The idea is compiling down into JavaScript is really hard if you want it to be efficient and fast. But if you compile down to WASM, then the browser can take the WASM and it can make it run very quickly and efficiently by, for the most part, just converting it straight into actual machine assembly code. So I'll talk a little bit more about how all of that works. So if all you can do is math, move around memory, and make function calls is the other thing. If that's all you can do, how do you actually do anything interesting? Well, turns out WASM is actually shoved inside JavaScript. And the browser adds a new API over here for WebAssembly. And so the way that API works is it takes this WASM, very basic assembly language, and it says, okay, if you move memory around, if you make this function call in such and such a way, I will connect you to a JavaScript object. So let's go ahead and take a look at the world's simplest WASM program. Okay, so here I have a very small example with a very small WASM program, maybe the smallest you will ever see. The actual WASM code is right here. It's encoded as base64. It's an assembly language, so it's going to be just a bunch of bytes. There's no good way to look at it. This is meaningless. I've created here, you'll see this kind of Lisp-like syntax used to represent WASM a lot. I don't know it, but I kind of made up something that looks kind of like it, and it'll describe what's going on in here. So basically, I've created a module. There's one function, takes no arguments, returns nothing. It loads 42 onto the stack, essentially, and it calls a function named imported_func. And then it exports this function, is called exported_func. So import and export are native WASM features, and they're used by Chrome to be able to connect WASM to JavaScript. So you can import functions that you can then call. That's how WASM calls out to JavaScript. And you can export functions, and then JavaScript can make calls to those exported functions. So I take this program and I send it into the Chrome API, this WebAssembly thing. This is part of the Chrome API for WASM. I send it in, and it gives me back an object. That object will have that exported function, so I can make a call against that exported function. And that object, in order to compile, it actually needed my imported function. So when I make this call here, instantiate streaming, which I'm sort of passing it into Google, this is essentially a linker call. So when I'm asking it to link this program, I have to pass in import object, which has to have as an imports object all of the functions and things that I'm going to import into my module. So I pass in imported function, which is what we're calling here. An imported function is going to grab this p element from my document, and it's going to change the text content to whatever gets passed in. So when this all gets linked in, I get back this object, and this object has exports, and it has exported function, which is now a JavaScript function that I can call. So I actually connect that JavaScript function to my button. So my page has a paragraph which starts out saying no message from WASM, and a button that starts out disabled that says launch WASM. Once the code's compiled, I undisable my button, re-enable it, enable it. Once I click that button, it's going to call exported function. It's going to call this function here. This function will then call imported function. It's going to call this function here, and that will update part of my page. So let's go ahead and take a look. All good so far. No message from WASM. And I click it, and message from WASM 42. So that is the world's smallest WASM program. And you can actually see in Chrome this sort of WASM thing here. So function call 0. This is where it's calling imported function. This is where it's loading 42 onto the stack. And that's the completeness. So you don't actually see the exact same format, but it's pretty much, this is what that binary coded down to. So that is all well and good if you love writing assembly. We're not even going to get into what it would take to write a C# program in WASM, but we will take a little bit of a look at what it takes to write a C program in WASM. So I have a C program here. I have a main method which calls printf, and I have this int square root function which calls square root from the math library. Well, square root is pretty straightforward. That's just math, so that can compile down completely into assembly. Printf is not just math, that's I/O. So in C, you have a well-defined concept of the standard output stream and the standard input stream, and printf is going to be manipulating your standard output stream. So if you wanted to write a C compiler to take this and compile it down to WASM, you're going to have to invent a concept of a standard out and standard input so that your C program can actually run correctly. So there is a whole SDK, EM, SDK, EM scriptin. I don't know what exactly it stands for or whatever, but it's a C compiler for WASM. And when it compiles, it actually creates a JavaScript wrapper, which is quite large. And this basically is a fake OS, if you want to think of it that way. It adds all of the things like a standard output stream, standard input stream, the ability to read or write files a little bit. I don't know. I haven't looked through the whole thing, but It essentially is the JavaScript, a JavaScript operating system that our C program is going to get linked against when we run it. So I used that, I'm not going to go through that, but I used that EMCC program to compile it. It compiled it down to a WASM file and a JavaScript file. That JavaScript file set up all of this. So you can see here, for example, it is binding out in air. So it says blah, 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 which are how we can print a standard out and standard error respectively. So it's creating the standard output and standard error streams here, which it maps to, in the JavaScript world, console.log and console.warn. So I then go ahead and pull this in here. I have this wasm.html. I load in that hello.js file, and basically I just say, once it's done running main, then, and here's the next thing I want to do. I have this function here, int square root. I want to actually call this from JavaScript. So I've got two things. I've got main and int square root. And actually main doesn't work, but I'll figure that out another day. So I say, after it's done running, grab that function called int square root and create me a function wrapper. The thing is called int square root. It takes in a number and it returns a number. Or actually, it returns a number and it takes in one argument, which is a number. So this gives me back a JavaScript function that I can then call. So the integer square root of 150 is blah, and I just log it to the console. So if I run this, it turns out I can't actually run this the way I've been running it. The way I've been running all these examples is I open them up in Chrome. I go into Chrome, I press Control-O, and I open up the HTML file. That's all well and good for a lot of things, but this hello.js file is actually using XHR and the fetch, which are APIs that we're going to learn about later in the next video, for making calls against a remote server. Those functions don't work so well if you load it up as a file. So I actually have to properly serve this code in order for it to work. I'm not going to go into details of how that happens because that's something we're going to talk about a lot more later. But you'll see here I'm not going to just open the file. I'm going to go to localhost 8000 wasm.html, and this will load this thing we were looking at right here. And it's already done. There's no button I put in here. It ran in the console. WASM code finished. The integer square root of 150 is 12. So I couldn't actually get the printf to work. This was the example from the WASM tutorial. I must have made some step wrong or something. So it'll be a bonus exercise if anyone is bored, but I've exceeded the amount of time I want to spend on it. But I was able to make this call into my C function, int square root. You may notice the square root of 150 is not exactly 12, but in C, if you do an integer square root, it gives you back an integer answer. And that is WASM. So one last thing I want to talk about is not actually a scripting language, but you'll hear about it every now and then, and more. Signal R. Who really needs scripting? So you will see people say you don't need to use JavaScript, you can just use Signal R. This is something that we'll talk about more later, as I said, but let's talk about it now a little bit, because it ties into this debate that has been going on for ages, pretty much since people started writing JavaScript, which is how much should we do in the browser and how much should we do in the server? And you will hear all kinds of arguments. For example, if you do more work on the server, then you have to pay for bigger and better infrastructure to host because you're going to spend a lot of CPU time on the server. Whereas if you can push more work off to the browser, it's cheaper to host. But on the flip side, it's a lot more complicated to do it in the browser because sometimes the browser doesn't have easy access to all of your data. And it could be potentially less secure because now you have to write APIs to get your data, and those could be flawed, and it will go back and forth. The pendulum has swung both ways as long as I have been programming. So extremists on the do everything in the front end side are currently winning these days. If you go by terms of popularity, Stack Overflow, and that kind of thing. And the most extreme way is that even if I am clicking a link, which is something HTML should be able to do for me. I should click a link, I should make a call to the server to load up a whole new page. I should get a new fresh batch of HTML from the server. But if you're building a spa, even when you click links, it actually gets faked out. It does make a call to the server, but not to get HTML, just to get some data. And then it completely re-renders the HTML using JavaScript. So the server never has any concept of HTML. The server only really knows data. Signal R is on the complete opposite end of the spectrum. The idea with Signal R is I want to write no JavaScript and I want to push everything to the back end. So it takes advantages of tools like WebSockets and just HTTP2, more efficient communication. And it says, the penalty for making a call to the backend has gotten really small. So even if I'm not doing a lot of work, I don't see any problem with going to the backend to do that work for me. So here, for my example before in Stack Overflow, if I'm typing in the start of a tag, it's going to present me a list of possible tags. The do everything in the front end people would say, okay, I'm going to call an API method to get that list of possible tags, and then I'll probably cache it. I'm not even going to call it API method again. And from then on out, I'll do all of the actual creation of these elements. That JavaScript word right there and that arrays word right there, these are HTML elements. That's some kind of span or a div or a paragraph element, and there's some mark in there so it can mark which section needs to be underlined. All of that actual HTML gets rendered in JavaScript. Whereas Signal R says, oh, the user's typed script, I'm going to make a call to the backend, and that call is going to return those elements themselves. It's not going to return data. It's going to return the actual HTML itself, and then I'm just going to shove that in there. So the basic idea of Signal R is to push so much to the backend that you don't really even need scripting. So I bring it up in the scripting example because two major approaches are JavaScript and WASM, but there is a third approach, which is to do no scripting whatsoever or as little scripting as you possibly can. And especially with the C# crowd, that tends to be quite popular. Okay, so that's the end for scripting. Next, we're going to talk about transport, which is all about how we get data back and forth from the remote server to the browser. Thank you. If you have any questions, please ask them. If there's anything else you want me to cover, then please let me know, and I'll tack it on to the end when I get some free time.